Today we're going to talk about a word called entropy, and the problem with this word is that it looks very similar to a word we've been talking about in this chapter, enthalpy. So you have to be really careful to not mix those two words up. Enthalpy is what we've been talking about, the heat of the reaction, and the symbol for that is delta H. So the way I remember it is that enthalpy has an H in the middle of the word. So just think about heat having an H and enthalpy having an H, and the symbol is delta H. For entropy, this is a measure of the disorder of the particles in a system, and the symbol is delta S. So the key word there is disorder. That's what you want to circle or highlight. When you see entropy, you need to think disorder. In nature, entropy is always increasing. So if you had a deck of cards and you threw it on the floor, it's much more likely that it's just going to be a jumbled mess of cards than if it would land like this picture up here. So nature by itself is always going to go towards more disorder. And there's several ways that you can change the disorder in a system. One is by changing the state of matter. So solid is the most ordered. That's the particles are just kind of vibrating in place, and a lot of times there's even a pattern. For a liquid, they're flowing around each other, so there's a little bit more chaos or disorder, but they're still pretty close together. And then for gases, they're really far apart, bouncing around really crazy speeds. So gases are the most disordered. So for instance, melting, you would say the entropy increases with melting because you go from a solid to a liquid. The second thing you can change is the number of moles. And remember, moles are the particles, so for a reaction, you're going to look at the coefficients. So if you look at this reaction here, we have 1 plus 2 is 3 on the reactant side. 3 plus 3 is 6 on the product side. So we went from 3 moles to 6 moles, and the way I think about it is just like if you had kindergartners. If you had 3 kindergartners in a room versus 6 kindergartners, you're going to have a whole lot more chaos when you double the number of kindergartners. So the more particles you have, the more chaos there's going to be. And the last thing is temperature. Remember, temperature is a measure of the motion of the particles, so the faster they're moving, the more chaos there's going to be. Again, if you go back to the kindergartners, if you tell them to walk around the classroom versus to sprint as fast as they can, the sprinting is going to be a whole lot more disordered than if you have them just walk. So if you increase the temperature, the entropy will also increase. So let's look at each of these. If you go from a liquid to a gas, gas has more disorder. So we say that the delta S is positive because you're increasing the entropy. Solid to liquid, liquid is more chaos or more disorder. So again, you're increasing the entropy, so this one's going to be positive. If you increase the temperature, since it's a measure of the motion of the particles, you would also increase the entropy. So that's going to be positive. Dissolving a gas in a solvent means that you're taking the gas and turning it kind of into liquid. You're not actually turning it into a liquid, it's not condensing, but it's kind of in the liquid state. So it's going to be more ordered as a liquid state. So if you go from chaos to order, then it's a negative delta S. You're decreasing the chaos. For the next one, you're just going to look at the particles. So we have 2 on the left, we have 2 plus 1 is 3 on the right. So again, the more particles you have, the more chaos you have. So that's going to increase. And then the last one, when you dissolve something, there's 2 things you can look at actually. You can look at the particles. We went from 1 to 2. Or you can look at the states of matter. We went from solid to aqueous. Both of those show an increase in the entropy. So it's a positive because it's increasing the disorder. And the next thing we're going to talk about is spontaneity. So draw an arrow to the word spontaneous and just write that it's when a reaction occurs by itself. Spontaneous, when I say spontaneous, it means when a reaction occurs by itself. If it wasn't spontaneous, then you'd have to help the reaction go. You'd have to do something like heat it or do something to help the reaction go. And there's 2 ways a reaction can be spontaneous. One is if it's exothermic. Remember we talked about the fact that nature prefers exothermic reactions. So if you have a negative delta H, that's what nature prefers. And if you have a positive entropy. So if you have exothermic and you're increasing the chaos, both of those are the things that nature prefers. So if both of those happen, then you're going to have a spontaneous reaction. For example, wood burning, once it starts to burn, you don't have to help it burn. It's going to go ahead and burn by itself. And the reason is because it's exothermic, it's releasing heat, but it's also creating more disorder. So once it finishes burning, you have a gas instead of a solid because some of it's turning to smoke, and you have more particles as ashes than you did as the solid chunk of wood. So you're increasing the entropy and you're decreasing the energy because it's exothermic. And since nature favors both of these things, the things in red is what nature favors, if both of those happen, it'll be a spontaneous reaction. Joke of the day, Department of Entropy, so you can tell that his office is messy. And the last thing is just talking about how fast a reaction occurs. So first we need to review collision theory. We talked about this a little bit before. Just because two particles collide doesn't mean that they're necessarily going to react. There's two things that have to happen. They have to hit with enough energy. So if they're moving too slowly, they're just going to bounce right off each other. And then the other thing is they have to have the right orientation. So if they're turned the wrong way, they're not going to hit in the way that will help them react. So when we talk about the rate of a reaction, if I said how could you increase the rate of a reaction, you want to think about ways that you can have better collisions. So the ways that you can fit these collision amounts. We call it effective collisions. So there's several things you can do. We've talked about you could add a catalyst if you're trying to speed up the reaction. The catalyst lowers the activation energy, which means you don't have to have as much energy for it to actually react, so more particles are more likely to collide and actually react. You could heat it because then you're providing energy to the particles, so they're more likely to hit with enough energy. You could increase the surface area, and what I mean by that is if you take a sugar cube and crush it into little pieces, you're increasing the surface area, and it just allows more pieces to collide. So if you have a sugar cube, the little sugar particles that are trapped in the middle of the cube, they can't collide with whatever's on the outside of the cube. But if you crush it into little pieces, then they can all collide, and so you're increasing the collisions. And if you stir it, you can also make them hit each other more, so that's going to increase the collisions. And there's a cute little YouTube video. It's a cartoon. If you want to watch it, you can just plug this into your internet browser. This video just kind of goes over some of the ways that you can increase the rate of reaction, but it's pretty funny, and it's a good cartoon. So if you have time, go ahead and watch that. If not, take a look at page 7 in your worksheets, and you should be able to figure out if entropy increases or decreases, and just make sure you check your answers on those when you're done. That is all for today.